maximums, local minimums, inflection points, getting lots of information about functions from their derivative and their second derivative. And now we want to take a step back to something that I think in a lot of cases is actually a little easier. So here, what we want to do is global optimization, which means I don't care about local maxes and mins. I want to know that I have the very biggest y value for the whole function and the very smallest y value for the whole function. Okay, so just a definition to get us started, and then we'll look at some graphs. This is a pretty easy concept graphically. The trick, again, will be, what if you're just looking at an equation and trying to figure this out? So, our definition here is that if f of p is greater than or equal to f of x for all x in the domain of x, so this is what makes it different from when we had this at the beginning of 3.1, then f has what at p? Okay, so this is saying the y value at p is at least as big as all other y values, not just the nearby ones, all of them. And if that's true, then we would say f has a global maximum. I'm feeling like there's another name for this that I'm forgetting. Absolute. Relative versus absolute is another way to say this. So an absolute maximum is a global maximum, and a relative maximum is local. So I will stick with the global and local, but that is another way to say it. And then if f of p is less than or equal to f of x for all x in the domain of your function, that means the y value is at least as small, which means it's a global minimum at x equals p. Okay, so global max, global min, very biggest and very smallest y values. We get this handy extreme value theorem, and I want to look at some pictures and think about it. So the extreme value theorem says that if a function is continuous on a closed interval, then you're guaranteed a global maximum and a global minimum on the interval. So if we look at these pictures, we can just say, okay, here's our function, it goes on forever. That one should have arrows, as should this one. Do I have a global maximum? And the answer is absolutely yes, I do, right here. That is the very biggest y value that the function ever takes on. But if I ask, do I have a global minimum, the answer is no. And our immediate concern should be, if the extreme value theorem just told us that we are guaranteed a max or min, what's happening here? And the answer is, these are really specific conditions, so the function has to be continuous, and you have to be looking at a closed interval. All real numbers is not a closed interval, so if you're looking at all real numbers, there's no guarantee. You could have a global max or min, but there isn't a guarantee anymore. So if I was looking at all real numbers, I would say there is no global minimum. However, what we'll do is we'll often, not always, but often, we will restrict the domain. So we'll say, for example, this is my A, and this is my B, and I'm interested in the global maximum and minimum on the interval AB. So now I'm looking for, my dog is whining, don't mind her, I'll deal with her momentarily. Test stop. Be done in a minute. Okay. So my global maximum stays the same, although interestingly, if I picked an interval that didn't include the vertex, then I would change. I would not have the same global maximum I originally found. Now my global minimum happens right, oh, I didn't have it right, max. Global min. Okay. So there it is. We've got the closed interval. We get our global max and our global min. Okay, so let's look at this one, and let's start right off with A to B. And we're looking at the closed interval AB. And so again, we want to picture this as we cut it off with closed circles, and then we're getting just the stuff in the middle here, and ignore all the rest of it. Okay, so if I say, do I have a global max? The answer is yes. It happens at endpoint B. If I look for a global minimum, because these go forever and ever and ever, I don't have a global minimum. It's not okay to say negative infinity is a minimum. You can never get there, which means there is no smallest value. You keep going and going and going. Okay, so once again, our first thought should be, how did the extreme value theorem fail us? And the answer is, it didn't fail us, we failed it. This function is not continuous on our interval. So this is a great example. Any sort of weird asymptotic behavior is going to wipe out maxes and mins. So this one has no minimum, even though we have a closed interval. Third one, if we look at all real numbers, we will see that there is no max, and there is a minimum. It's right here. And once again, this is acceptable according to the extreme value theorem because the function is not, we haven't restricted the domain to a closed interval, if I can remember what we're doing now. Okay, so let's look. So this is for all reals. If I restrict the interval, restrict the domain down, let's say I go from A to B. So now I'm looking only at this chunk. So this is for A, B. Now I have my maximum right here and my minimum right here. So depending how you set these intervals, it will change your answer. Okay, last one. This is supposed to look like a sine wave. If it is a sine wave and we look at the whole thing, one question people have is, for example, if this is up at y equals 1, what happens if you hit that value over and over and over again? And the answer is nothing. It would still be your maximum. If you look back up at our definition, we just needed the y value to be at least as big as all the other y values. It's okay if you hit that same y value again. And then our min would be at -1. What I really wanted to look at here besides that was, what if we do an open interval? So let's say we go from A to B, and A is right here, and B is right here. Okay, so open circles at A and B, and we keep this chunk in the middle. Okay, so maximum, I guess I didn't need to scratch that out. We do get a maximum, it's right there at the top. For minimum, this one's really interesting, it messes with people. Let's say the y value of that open circle is 0.2, just pretend. If I'm trying to say there's a local minimum, the answer here is no, there is no local minimum, and the reason is this. You have to be able to tell me what the smallest y value is. Here, if you said the smallest y value was 0.2, you would be wrong because I never actually hit the y value 0.2. So maybe you would say it's 2.1, and you'd still be wrong because I can get smaller than that. I can use 2.01. So then you might try 2.01, and I go even smaller, 2.001. So if the point that looks like it's going to be the minimum or the maximum is at an open circle, then there is no max or min. And that, again, is okay with the extreme value theorem because it requires a closed interval. So this function is, we call it bounded. There is absolutely a value that it doesn't go below, but it doesn't have a minimum. It doesn't have one value that is the smallest. Okay, so to finish off this video, what I want you to notice is that when we found a max or a min, this one was at a local max as well. So the global max was at a local max. So how about if we say it this way? It's at a critical value. The minimum's at an endpoint. Here, the max is at an endpoint. Here, the minimum's at a critical value. The max is at an endpoint. Or when we did all reals, the minimum was at a critical value. Here, the maximum's at a critical value. So what I hope you're seeing is that if we're looking for a global maximum, all we really need to check is all the local max and mins, and we don't even have to be that picky, just all the critical values, which may or may not be local maxes and mins, and then any endpoints. That's really all we have to check. So it's really simple if you have all the conditions of the extreme value theorem satisfied. So if you're trying to find a global maximum or minimum and your function is continuous and you have a closed interval, you're just going to look for all the critical values, and then you're going to evaluate your function. So plug in each critical value and each endpoint, and then you're just comparing y values. So there's no plugging things back into the derivative, and this is my biggest warning for this 3.1, 3.3 stuff, is just be clear what you're plugging into and what information that's giving you. So here, we make a really short list of critical values and endpoints, and then since what we want is the biggest and smallest y values, we just check the y values. That's all we need. We don't check increasing, decreasing. because I don't care if it's a local max, I only care if it is the absolute biggest y value or smallest y value. What gets a little tricky is if you violate either of those conditions on the extreme value theorem, you have to really carefully check what's happening where you're violating the extreme value theorem. So if you have an open interval or an open-ended interval would be the same idea, or if your function is discontinuous, you're still going to find all the critical values, but then you're going to have to evaluate your function at each of those and at any closed endpoints if you have any. And then the additional step will be anywhere you violate the extreme value theorem. So you have an open endpoint, you have a discontinuity, you have an endpoint that goes off to infinity, you have no endpoint. You're going to use limit thinking to try and figure out what the function is doing near that point. Is the y value headed off to infinity, in which case you'll have no max? Is it headed to negative infinity, in which case you'll have no min? Is it an open circle that's smaller than any of your y values, in which case you have something like this example right here? So that's our basic strategy, and I will walk you through a few examples. Thanks.